Okay, so the example that I want to talk about is the geometric series, just to give you all the formality. So it's the geometric series. So remember, how is this defined? So you take any number, say r, and then you consider the sequence of all its powers, and you take the series of that. So you get this. The sequence is set of r to the n power, n is bigger than or equal to 0. So what does that look like? Well, r to the 0 power, take any r, let's say not equal to 0, so gives you 1, then the next number is r, the next number is r squared, next number is r cubed, the next number is r to the 4th, on forever. And so the geometric series is this summation. So it's the summation n goes from 0 to infinity of r to the n power. So again, that just looks like 1 plus r squared plus r to the 3rd power plus on forever. So the question is, does this converge? So the question is, does this converge? And the answer is, it depends on r. So it turns out that it depends on r. And in general, if you have a series, the first question you ask is if it converges. And unfortunately, usually that's the only question that you can answer. You can say, yes, it converges, or no, it does not converge. In the case of the geometric series, we can answer the question. For certain values of r, it does converge, and we also have a very nice formula for what the actual what it converges to, which is really nice. And so let's just go through the definition one more time. So remember, how do we do it? To see if it converges, we have to calculate the partial sums. That's in the red box here. We have to take these partial sums. So instead of summing over the first infinite terms, which doesn't even make sense, we sum over the first n terms, and then we take the limit as the number of terms we're summing over gets larger and larger and larger and larger and larger. As long as it's a finite sum, we're getting a number, so we're just taking a limit of a bunch of numbers here. So each of these things is an actual number in green. Finite sums give a number, and so you're taking a limit over an actual number, and you want to see if you get this number L. All right, so let's go through that carefully. So in this example, Sn, well, I'm going to write it a little bit differently. I'm just going to go out into the power of n. So I'm going to say Sn is 1 plus r squared. I'm being a little inconsistent, but let's just define it to be that way. So I'm going to sum up to the power of n. So they're actually n plus 1 terms, but that's okay. Everything will still be fine. And so there's actually a nice formula for this, and there's actually a nice formula that we can write down. And to write down that formula, we just have to do a little quick calculation. Let's pause for a second. So notice that if you do 1 plus r squared plus r to the nth power, and if you multiply that by 1 minus r, so the way we'll multiply this is we're actually going to distribute the terms here. So if you distribute from the right, you get 1 distributing over all of that stuff. So that gives you 1 times 1 plus 1 times r plus 1 times r squared plus times 1 times r to the n power. So I distributed over the 1 first, and now let's distribute over the negative r. So that gives you negative r times 1, which is negative r. That gives you negative r times r. That gives you negative r squared. Negative r times r squared gives you negative cubed. And you keep going, and the last thing you'll get is negative r times r to the n. That gives you negative r to the n plus 1 power. So now, if you just look at this, you can see, or you can convince yourself, that all of the terms cancel except for the very first term and the very last term. So this gives us this very beautiful formula. This is equal to 1 over r to the n plus 1. And so if we just take this equality here, then we can take this equality here, and we can solve for the yellow box. And we just divide both sides by 1 minus r, and that gives us this very nice formula for the partial sum, which is written above. So I'll write, so the formula is the partial sum is r to the n plus 1 over 1 minus r. So you have this very, very nice formula. I'll put it in a box here. This isn't true in general. This is just for this one example, that if we want to sum up the first n plus 1 terms of the geometric series, there's a very nice formula for it. Okay, so now if we wanted to actually calculate this geometric series over here, our goal is to calculate this geometric series. Let's go through the formula one more time. We'll keep the formula over here. So the summation, n goes from 0 to infinity, of r to the n power. If we go to the definition, by definition, that means we have to take the limit as n goes to infinity of summation of, say, I'm going to say k now, is equal to 0 to n of r to the k. I'll just write that out explicitly. So we're taking the limit as n goes to infinity of 1 plus r squared. We keep going until we get r to the n. That's formally what this thing is. We have to take the limit as we're doing a finite number of sums, summing over the first n plus 1 terms. Doing a finite sum here, but we stop it here. But now we're taking the limit as the stopping point gets larger and larger and larger. So you're summing over 5 terms, then 6 terms, then 7 terms, then 8 terms, then 9 terms. We do this on forever, ever, ever. But now this thing in parentheses that I just underlined in yellow is exactly what is written over here. So we have a nice formula. We're just going to use that formula here. So this says that the summation of the geometric series, sum n goes from 0 to infinity of r to the nth power, is equal to the limit as n goes to infinity. And now the thing that I just underlined in yellow is given by this formula here, 1 minus r to the n plus 1 over 1 minus r. So in order to evaluate this limit, we can see right away that, so there are a couple of conditions here. The first thing is that r cannot be equal to 1, otherwise we'd be dividing by 0. And the other condition is that the absolute value of r, so this is since we can't divide by 0, and the other condition is that the absolute value of r has to be less than 1. Otherwise, else this r to the n plus 1 power gets huge. So inside the limit here, as you can see, inside the limit, we have this r to the n plus 1 power. And so if r is bigger than 1, then or, smaller than negative 1, so if r is like 2, then you're doing like 2 to the billionth power. That's huge. Or you're doing like negative 2 to the billionth power. That, that's going to be, also positive, or it could be negative, but it's going to be a huge number, either positive or negative. So the conditions, in order to actually take this limit, are given right here. So these are conditions. Obviously r can't be equal to 1, else it doesn't even make sense. And if we wanted to take the limit, then we need the absolute value of r to be less than 1. And then when you're taking a huge power of it, then, if you take like the number half, a huge power of half gets really, really small. So if we do that, when we take the limit, it just goes away. And that's what we get. Okay? So we have a formula. I'll rewrite the formula, but I just want to illustrate the process. So the geometric series, if you pick any number except for 0, otherwise it's just stupid. If the number is 0, then it's like 1 plus 0 plus 0 plus 0, so that's fine. But take any number other than 0 and consider this series here. We want to see, does this converge? And the way we do that is formally, let's come back down here. To actually do it, you have to take the limit over the partial sums. And above, we derive this formula for what the partial sums are. And so if we implement that formula. So anyways, in summary, we have the geometric series summation n goes from 0 to infinity of r to the n, which is 1 plus r squared on forever, is equal to 1 over 1 minus r if the absolute value of r is strictly less than 1, otherwise it's 0. Sorry, otherwise, I misspoke. Otherwise, it is divergent. So remember, the original question was over here, does the geometric series converge? And so the answer is yes, it converges for r less than equal to 1, absolute value of r less than equal to 1. But even better than that, we actually derived a formula for what it converges to. So this is very, very nice. So in summary, the geometric series converges when r is less than 1, and otherwise it's divergent. But not only that, we have an explicit formula for what it's equal to. So just as a simple example, if we wanted to do the summation, n goes from 0 to infinity of 1/2 to the nth power. So here r is a half. So it's in the correct range. It's absolute. It's already positive, and it's less than 1, so that's great. But so if we want to do that, the formula says that that's equal to 1 over 1 minus 1/2. So give them a common denominator. That becomes, well, just 1 minus 1/2. 1 minus 1/2 is 1/2. And of course, that's equal to 2 over 1, which is just 2. That's an example of this formula here. Another example is if you wanted to do summation, n goes from 0 to infinity of 1 to the n power. Well, here r is not less than 1, and so we see that this diverges, but that's 1 plus 1 plus 1 plus 1 plus 1 on forever. So this clearly diverges. And we can see that r is not less than 1 in this example. So it doesn't satisfy the condition we need. So it clearly diverges. Another example is if, say, summation goes from 0 to infinity, let's say of 3/4 to the n power. So that would be 1 minus 1 over 1 minus 3 over fourths. So that's equal to 1 over, so that just becomes 1/4. 1 minus 3/4, so that's equal to 4. So it's crazy that we actually get these finite summations here. So, yeah, so just for fun, we can, so for example, this one here, it's like saying if you do 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, but if you do that, you have to go literally on forever. You don't ever stop. And theoretically, you would end up getting the number 2. So it's very strange because, how do you go on forever? But if we could go on forever, we'd actually get the number 2. If that makes sense. So that's just a quick introduction to series.